Hello, everyone, and welcome. Thank you for joining us here today for this Ask the Expert session on KV Cache. My name is Stephanie Giard, and I'm the Senior Product Marketing Manager here at DDN. And I am joined by Joel Kaufman. Joel, can you please introduce yourself?
Sure. Hi, everyone. I'm Joel Kaufman, and I work as an outbound product manager here at DDN, focused on AI infrastructure, and how it can help accelerate our customers' needs.
Fabulous. I appreciate you joining me here today. So we're here to talk about KV Cache, and KV Cache is a really hot topic right now in AI. The analysts are telling us that starting as early as this year, AI inference workloads will consume more compute than training. That's a lot. This obviously raises some concerns, both because of cost and also because of energy consumption. But it was interesting. When I was at Supercompute in November, what really surprised me was that even people deeply experienced in HPC and AI were coming by the booth, and I could tell they were still struggling to understand what KV Cache is and where it fits into inference. So that's what we're here to talk about today. With inference on the rise and some real confusion in the market, let's start at the beginning. Why should we care about KV Cache, and what exactly is it? How does it impact DDN customers?
Yeah, so here's where I think some of the confusion is coming in. For a while now, we've been talking heavily about training and things like that. And that's becoming a very well-known type of workload where it feels like it follows a lot of the same characteristics as like traditional HPC. You have, lots of speeds, lots of feeds, big read types of functions that go in there. And then similar to HPC types of workloads, you have checkpointing and things like that. That's been well known. And now that we have all these big foundational models out there, the problem is that the knowledge transfer of moving from that first stage of training out to that second stage, which is inference, how do you actually apply these models and get into, say, a generative AI or an agentic AI type of environment where you're actually going to use the information and get it out to the end users, it's really becoming this next critical thing. In fact, one of the things I really would like to talk about a little bit here, and I'm actually going to pull a slide up. I don't do this really often, but here's kind of what we're seeing. And I think at Supercompute, this might be what you're running into, which is that we've started with a group of customers and a group of users that start on the far left side. You have HPC simulations and data pattern work and all the various challenges that are associated. And you move towards the right side, where it moved from that level of simulation up into research data, and then beginning to build on that with how do you deploy these models and get it going. And now we're at the far right side. And that far right side is really where KV Cache comes into play more and more, because now you're talking about the idea of creating use cases that people will directly query your models. And then how do you get the highest levels of performance coming out of those models so that you get real results that are much faster than it would be if you didn't have this type of KV caching in place. And I think we'll explain in a little bit maybe what KV caching is, how it behaves, and things like that. But as you can see that, go ahead.
Go ahead.
I was going to say that move from HPC on the left all the way over to the right. It's funny that an awful lot of the data needs are really similar, but people don't realize it yet. And so they're trying to figure out where that matchup is.
Excellent. Well, and I appreciate you popping in a slide like this. I think it's helpful to visualize when we're talking through this exactly how this looks. So many of the people watching this are HPC specialists, and those are the kinds of people that I was talking to at Supercompute. But across their organization, they are seeing more of these inference workloads, like you were saying, moving from left to right. So what happens if they don't use KV cache? What are the ramifications? What does it look like when they do have KV cache?
Yeah. So we're going to get a little more technical here on this. And what I want people to understand is that I talked about the I/O patterns and how data flows through the system being somewhat similar for HPC through an AI pipeline. For training, that is 100% true. When it comes to that inference, though, there's actually some nuance there that we want to be really, I guess, a little careful about. So what we look at is this. During inference, you actually have two different complete stages. You have what's called prompt and prefill, and that's the idea that it takes whatever your query is, your prompt, creates sets of tokens, and then those tokens are computed and put into this cache. And then the second half of this is that once you have these tokens put in from the prompt, then you have all your AI tools, they query the model, they try and figure out, they associate data with what you're trying to get to. It's called computing attention, and then figuring out where things live. And then it decodes all these tokens that you've put in the cache and gives you a response out. And so these two separate layers, what really happens here is that KV cache acts like a memory structure. And so what I mean by that is without that KV cache that's in place on the screen there, it would have to continue to recompute and recompute and recompute all the attention for all of these for every single query that came in.
That would get excessive.
It would be huge, right? Because what it really will wind up doing then is it's going to begin to move the performance structures or the performance of the system. It's all in compute. And so you're burning a lot of GPU cycles, a lot of CPU cycles to continually do this, and latency goes up because it has to constantly recompute as it does this. Now, by putting KV cache in, it says you compute it once, it stores these key value pairs, and then it says I can go just refer to them again and bring the data down. Now, in a simplified world on a single GPU where you're running your entire pipeline, maybe you hold this on local storage, right? But it's still local storage now that's taking the place of some of your memory cache. Okay, so it's good. You have, during that prefill stage, you have a whole bunch of writes that are happening to the system. Sometimes, a gigabyte a second. Doesn't sound too much if you have a single GPU, but if you have multiple GPUs, it gets a lot worse. And then on the decode side, it's reading from that cache and getting the data back into compute to give you your answer. And that's where you can see 3, 4, 5 gigabytes per second of reads, depending on the complexity of your query, depending on the complexity of the answer, all having to come out of this cache. And so really what we're looking at now is this idea of storage beginning to take over the workload from the compute side in order to make this happen. Let me throw up one additional slide here. Okay. It's not, so this is the use case for a single GPU, right? But what if you have like a big farm of GPUs, NVIDIA DGX systems, partner systems running all of their compute? Well, now you may have a type of GPU handling the prompt, a different type of GPU handling the response because they're optimized a little better. Maybe you just have a large farm where you're sharing this. Well, now you can do things like create a singular global cache for all these KV responses so that no matter which GPU actually takes the prompt in or the response, it can all access this as like a universal large pool. So
okay, so then your KV cache is acting more like storage. If you're using something like NVIDIA's Nixel or Dynamo, and the parallel file system that you're used to for HP storage, right? It's so that this is where
exactly,
then
This is exactly
Okay,
correct.
I'm getting it as you're talking through this. I'm getting it, which is Joel, which is why I really love to talk to you about this stuff. And once again, I appreciate you coming out to discuss this with me. So this is where storage becomes the enabler for inference.
Yeah, it really does. And like you said, the parallelism to a parallel file system is really true here. You're going to have a lot of clients being the GPUs, and if they want to access a common pool of storage or a common pool of cache, they all want to talk to it at the same time in a largely distributed and disaggregated manner. And so what you've been used to in running a parallel file system like EXAScaler really maps well here, because the exact same value proposition that you have, distributed, common access to the really high performance pool to get you all the information you need out to these high performance GPUs at the same time, that's it. So you nailed it right on the head.
Well, that explains why everybody's so excited about it. And as we've reached out to our customer base to talk about it, we've just seen more interest in this than anything else we've seen in a while. So it's an exciting topic. Well, let's tell me a little bit about which workloads are benefiting most from KV Cache.
Yeah. So if we go, so let's be very clear. Remember, I talked about that slide at the very beginning. And in fact, let me flip back to it real quick.
Okay.
There's the difference between training and inference, right? And really what we're doing is we're saying this is on the inference side. So when you're talking about any sort of inference workload where you're looking for really low latency, and you're talking about an environment where you want to get the fastest response, that's really where you want to trigger this. And that could be across multiple use cases, right? I don't care whether it's a basic chat bot that you're trying to get a quick response out of, or maybe it's a financial services type of environment where you're trying to process and use compounded and complex agents to try and get a decision augmentation type of system in place where.
So for agents too.
Yeah. Well, exactly, because agentic inference just means you're talking to a really specialized type of inference agent that will then query a whole inference pipeline. And so low latency, financial services, life sciences, manufacturing Q&A, quality assurance Q&A, basic research tasks, all of it becomes very sensitive to getting that highest performance out the door. So I think anytime we're thinking about KV Cache, think an inference output type of pipeline, not a training model. And that's really where it's going to fit in really well.
Okay. Let's talk then about some real world results. So what is the scale of the efficiencies and how does that translate into dollars? Because I mean, that's what it comes down to. That's what people are interested in, right? They're interested in dollars, and then they're also interested in speed and keeping their customers happy and growing their business.
Sure. So as we talked a little bit earlier, in this particular model of KV Cache, you have a choice. You can either sit there and keep recomputing and recomputing and recomputing, or you can go ahead and do that caching of the data of the KV pairs and get it so that you're doing less compute and more storage level functions. But this actually has, again, like you said, real world outcomes. So we had a customer, we have a customer, fairly large. And what they basically did is they're using a llama model in place as their core model for doing inference type of work. And as they continue to do more and more work and they add agents, et cetera, what we found is that the difference between them not using KV Cache versus using KV Cache, we saw approximately a 20x faster speed up in terms of their time to get to the first token, so maybe I should back up a tiny bit. time to first token generally is a well-recognized metric for how to measure the efficiency and the performance of getting a response out of the system. It's how quickly it can compute that part of the decode and get it out to the whatever the response mechanism is that goes out to you as an end user or out to an agent. So when we see this, the fact that it can pull from storage really fast without having to recompute, we are seeing approximately 20x faster responses. And in some cases, if we go a little bit farther back to a slightly shorter prompt, the number gets even higher. But 20x is a pretty good average across the board there.
Well, and that's going to make a huge, that's going to make a huge difference both for the user and the experience that they're having. But exactly. Do you want to talk a little bit about the costs?
Yeah. So this particular customer, and let me be very clear, they're a big customer, right? They're dealing with a farm that is quite large, and in terms of like 100,000 GPUs. And what they saw is that with that efficiency, so with the efficiency that they've seen, so they had an initial expenditure in terms of the number of GPUs, the ongoing cost, power, cooling, but the fact that they're able to respond faster, they're able to get the tokens out really fast, saturating the GPUs, making sure that they're not sitting there just spinning their wheels, recomputing all the time. The end result is that the overall user throughput dramatically went up. And so instead of waiting for time, they saw 60% greater improvement in terms of the efficiency of using their infrastructure. And they realized pretty quickly that over 3 years, instead of having to expand the infrastructure dramatically in terms of that compute footprint, they can sink that fixed cost in on the storage and on the GPUs and see approximately $100 million in savings by not having to continue to expand more and more infrastructure to get the exact same results. And by the way, this is a combination of a little bit of our research and information giving back to them and them telling us directly the types of efficiencies and savings that they've measured and they've seen.
That is impressive. And once again, this is why everybody's so interested, right?
Yeah.
Because it just can make a huge difference in your customer experience and also to your bottom line. So what do teams do next? Oh, you know what? And before I get into that, before I get into what do teams do next, please, we are going to be answering all the questions that people have. If we can do it now, we'll answer them now. Otherwise, we'll follow up with people via email. Make sure that your questions get answered. But please go ahead and type in any questions that you have, because that's why we're here. I'm here to have a conversation with Joel. I always learn a lot when I'm talking to him, but we're here to educate all of you as well. So please type in your questions and we'll be happy to answer them. But going back to where we were talking about what's next. So what do teams do next? This is where the folks at SKO were just kind of stuck that I was talking to. They were like, well, okay, I've heard about KV Cache and that's interesting. And I've got EXAScaler. We have EXAScaler, at whatever company they're at. And how do what do I do next to actually move forward with seeing these kind of time savings and cost savings?
Sure. And I think you meant supercompute, not SKO.
Oh, geez. That is exactly what I meant. Supercompute. RSKO.
Exactly.
That's something different.
I know. We've been a little busy behind the scenes. So I think the answer here is pretty simple. If you already have a DDM system, especially EXAScaler that's running, it's actually reasonably simple to go ahead and carve out a chunk of space on that EXA system and assign it to a KV Cache environment. And we're going to be having a webinar, a follow-on webinar with some really deeper details with one of our key customer engineers who will discuss really how you do this, all the little implications and things about where the rubber meets the road. But we're going to do that in a few weeks. But doing it isn't as hard as you think. And so step one is, if you already have an X and you already have space, use it, right? I mean, the infrastructure is in place. You don't need to buy anything new, really, except just make sure you have the capacity that's available. The second one is, I would say, contact your DDN account team. We have a large number of experts that are out there. If you're still kind of curious and going, I'm not sure, can you give me some best practices? Can we make sure to get things going? They're there to help you out, right? Whether it's bringing in professional services, whether it's having one of the pre-sales SEs or sales reps help you come to a conclusion about where and when you should deploy. And I think the biggest one, and this is me coming from, I used to be in operations, I used to be a sysadmin and all this, and I used to run some teams years and years ago. But overcome your friction within your own company or organization's environment. A lot of times you have people have different groups where one team will own the networking, one team will own application sets, maybe one team will own storage, and they have to work together to make sure that you have everything in place. Now, if you already have an existing DDN system, odds are you probably already having these conversations. But if you don't, getting that together will make your life a lot easier. And this is another reason where DDN can come in. We can bring our field experts to bear and help you have those conversations so that everyone can understand the full needs of the organization and bring you that really kind of unified solution across the board, especially for KV Cache in this case.
Perfect. All right. Joel, you ready? We've got some questions.
Yeah, I saw something pop up in the Q&A posts. What do we have?
I can read these out here. So if you're storing all of these KV caches, how much space do you need? Are there any issues with that?
Yeah, that's a really good question. And I think we're going to get into like some really deeper technical parts of that in the next webinar. But the answer is that as you generate all sorts of these tokens and the prompts come in, depending on the length of it, as well as the number of different prompts that come in that have to be done, you will see your space grow fairly dramatically in some cases. In a small environment where maybe you have some dedicated, like single GPU threading, a couple terabytes, maybe, could go bigger depending on the number of workloads. In the big environment where you're doing this distributed, say that 100,000 GPU data center, you're looking now at hundreds of terabytes, if not potentially petabyte scale in this case. And let me be very cautious about this. It is going to sound like the worst weaseling out here, but it depends. Because until we understand more about what your prompt space looks like, how long they are, whether you're doing cascading prompts through various agents versus very simple chatbot types of things, it's a really hard thing to compute out. But in general, a smaller environment, think terabytes. Really big environments, think hundreds of terabytes and up from there.
Fabulous. All right. Yeah. Next question we have here. Would KV cache traffic compete with training traffic on the same EXAScaler system? That's a good one.
Yeah. So this is actually really interesting. So if we're going back towards like that HPC space, you have an existing system and you want to use it. Well, there's a couple ways you can look at that traffic. The first one is that if you're using the same GPUs that are doing training and then you're partitioning them out and doing some of it for inference, then yes, you're going to have competition in that space a little bit. If you have dedicated systems, one side for training or for classical HPC, and then you have other GPUs that are being used for inference, then it's actually, I think the answer is really interesting. EXAScaler in the latest versions have multi-tenancy, including QoS functions built in. And so we can actually go ahead and segment the traffic using the existing environment you already have. And you can say, I'm going to give a certain portion of it to and dedicate it for the traditional classical types of training things. And then we can also segment it and isolate the inference side. And so you won't have a lot of competition there at all. You just need to make sure what you prioritize in terms of who gets the most performance depending on your needs. So it's fairly flexible in terms of what you do.
Questions, like I said, if we don't get to your question, we will follow up with you, try to get some more answered. But I want to take this time for a second just to say, Joel, thank you so very much for joining me here today. It is always a learning experience. I always come out smarter for the conversations that we've had. And
my pleasure. Glad to be here.
And I want to thank everybody out there in our audience for taking time out of your busy day to join us for this discussion. Thanks a lot.
Fantastic. Yeah, thank you.